express log 2u, it's sufficient to express the ceiling on log u. So the number of bits I have in here is log 2, let me just eliminate that subscript, log u, number of bits I have here is log u plus 1, excuse me, ceiling plus. So the total number of bits I'm spending here is 2 ceiling log u plus 1. And then the number of bits I'm spending here is ceiling log 2. So now the total number of bits that I'm spending is ceiling log 2, ceiling log u, plus 2 ceiling log u plus 1, which is less than or equal to log u plus 2 log u plus 4. So I take the 1 out of here and 2 out of here. So that's good, because now, as u becomes large, the scales of log u, because log u vanishes with respect to log u. So this whole thing is order log u, and the constant is 1. So that's exactly what I want. So the only point of this is to point out that there exists a prefix-free way to express an unboundedly large integer that has order log u bits, or excuse me, that is log u bits plus something that is of a smaller order. So let's make that statement. We can express an unboundedly large integer with, at most, log u plus 2 log u plus 4 bits. Now, that's not the most efficient possible representation, but it's good enough, because all I'm going to care about is that this is growing as log u, and that this term doesn't grow that fast. So I could, again, use the same bootstrapping trick to again, re-encode the log term, and then I'd have a log term, and so on and so on and so on. But this is good enough. Okay, so now we come back to address the point of what I'm doing is I'm basically encoding integers. So my encoding, my prefix-free code, excuse me, what I'm encoding is a series of integers. That series is u1, u2, u3, and so on, where each of these values is the position of last occurrence of a given string, of the current string in history. So I need to know the statistics of these u's. So basically what I've done is I've taken the source and I've transformed it into these u's. These u's can then be encoded in binary using this many bits in a prefix-free way. So it's there's sort of a two-step encoding here. Source, integers, and then integers to prefix-free code like this. So the question is, what are the statistics of these integers? What we're going to show is that, well, basically, what is this? This is the amount. This is encoding the amount of time you have to wait before a string occurs again. And what we're going to show is that, informally, we're going to show that UI is the recurrence time, let's call it R, of some string x from 0 to n-1. So remember, we're encoding length n strings, and we're trying to look back in time to find when that last occurred. So let's say this occurred, it occurs now from time 0 to n-1, and u is the amount of time I have to look back in the past. So, so in other words, what this is saying is if r x0 to n-1 is equal to u, what that means is x from n-1 minus u1 to, excuse me, x from minus u1 to n-1 minus u1 is equal to x0 to n-1. And in particular, there's no smaller value of u1 for which that's true. So what we're going to show is that r of x0 to n-1, the expected value of that is basically equal to 1 over the probability of x0 to n-1. So intuitively this makes sense. What this means intuitively is, okay, if you have a dice with 6 sides and it's a fair dice, you would expect each number on that dice, if you roll a 3 now, then the amount of time you would expect to wait until you roll another 3 is 6. Similarly, if an event occurs 1% of the time, then you would expect the expected amount of time that you'd have to wait for that event to occur again would be 100 time instance.